Hi, hello everyone. So welcome to this channel once again. So today's topic is on engineering, but not exactly on STAT or any other software, but it's on the essence of the engineering. So today's discussion is on the recent devastating earthquake that rocked Turkey and Syria. So we will try to understand mainly on several parameters from the structural failure perspective. So we will also try to understand why so many buildings collapsed in this region. So before I start off, firstly, I would like to send my heartfelt condolences to all the bereaved families who have lost their dear ones. So may God rest the departed soul in peace. Okay, so on 6th February 2023, a very catastrophic earthquake with multiple aftershocks struck the southern and the central part of Turkey and some portion of the western Syria. Now, this earthquake event was one of the deadliest and the strongest one in the Turkish history since 1939. That is Erzincan earthquake, if I'm pronouncing correctly, of the same magnitude. Essentially, there were two main shocks. One is 7.8 magnitude and another is 7.5, although the 7.5 is also considered as the aftershock. Now, the agency like USGS measured the magnitude of 7.8, which has the epicenter of around 34 kilometers west of the city called Gaziantep in the Gaziantep province, which is very near to the Syrian border. So you can see here, this is the historical record of some of the deadliest earthquake in this region, and this current one is one of the deadliest one in terms of the number of casualties. So this earthquake can be classified as a major earthquake, that is the magnitude is in between 7 and 7.9. So to understand how powerful the jolt was, we can see that the first one was roughly equivalent to the energy released from an explosion of around 5 million tons of TNT. And the second one was also close to around 3.5 million tons of TNT. So you can imagine how big and the magnitude of energy thus released from this earthquake. So some reports says that around 12,000 or more number of buildings are collapsed in this earthquake in Turkey, including many public infrastructures and some of the World Heritage monuments. Now, the building collapse of such huge scale in this densely populated region where this earthquake has struck, uh, that has added to the huge number of casualties. So there are several heart-wrenching footages and the pictures are coming in from various sources and various regions, showing the victims, including the children and the elderly, are trapped and crushed under the debris of that collapsed buildings. So really, it's very painful to watch them. Now, these scenes are so horrifying and bone-chilling that we can't even express here. So this is one of the drone footage. You can see that few portion of the cities and some of the neighborhoods were completely leveled and reduced to rubbles. Now, in response to that, most of the nations and some international communities have quickly come forward for the support and provided the SOS aid up to their capacity. Now, the official death tolls that is coming from various sources till I'm creating this content is around 28,000 and it's still counting. So it's very devastating. Okay, now this region of Turkey and the part of Syria is highly susceptible to the earthquake as the country is sitting on three tectonic plates and the nation witnessed several earthquakes in the past out of these seismic fault lines. So the built-up stress over the hundred of years which has formed from this tectonic plate movement has suddenly released. So today we won't go much into the discussion on the geological phenomena or tectonic plate movements or the cause of the earthquake because that's a separate thing. But today we will be more focused on some engineering part, that is the structural part, which has been the cause for this catastrophic building damage. So we will see what is the cause of the destruction of this building up to that scale. So in general, from several news or some other sources, we generally hear the seismic activity being measured in terms of kind of Richter scale, or in some of the similar scales are also there, like Mercalli scales and so on. Now, these scales basically indicates the amount of the equivalent energy thus released during the seismic action. So this is just an absolute quantity to understand the measurement of the energy released during this entire seismic event. So basically, for a layman to understand how powerful the earthquake was, these Richter scale or this kind of magnitude are very much helpful. But for a structural engineer, for evaluating the demand and the strength of the structure during this earthquake event, these scales barely matters, but rather the structural engineers look for working on the parameters like the peak ground acceleration, peak ground velocity, spectral acceleration, and so on. So we gathered some information from several sources, some expert opinions, some official agencies, and come to some point to understand the primary reasons behind this catastrophic building damage, which led to a huge life loss. So the first point is the PGA and the spectral acceleration. Now the PGA is known as the peak ground acceleration. So when the earthquake hits, the ground is subjected to the rapid shaking, and the peak acceleration thus experienced by the ground is known as the peak ground acceleration. Now, during this earthquake event, the strong motion data is recorded by the seismograph against the strongest tremor, that is 7.8 magnitude at different stations. But these are some of the preliminary data that were fetched from various stations, and depending on that, a different set of analysis were performed by the seismologist and the structural engineers. For example, this is one of the data that is collected from one of the stations. You can see here. These are the different seismic responses. The first one is the acceleration response, second is the velocity, and third is the displacement response. And all these are the ground motion data. And these ground motion data can be converted into the corresponding spectral acceleration. So this plotting is performed by using different numerical technique and the computational procedures by which you can convert the seismic historical data into the spectral acceleration data. So this is the plot of acceleration versus the natural time period, and all these data correspond to a particular station. Now here you can see that the peak ground acceleration, that is the PGA, was recorded at around 0.7 g, and the maximum spectral acceleration is around 2.1 g. Just to let you know that this g is generally used for representation, which is the acceleration due to gravity. So the seismic acceleration is normally represented in terms of g or as a percentage of g. So don't get confused with the peak ground acceleration, that is the PGA, with the spectral acceleration value. The spectral acceleration means the acceleration exhibited by the single degree of freedom system, that is the SDOF system, having certain unique natural frequency or natural time period, which is subjected to the said earthquake ground motion. And the peak ground acceleration, from its definition, it signifies that the peak of the acceleration exhibited by the ground during the entire earthquake event. So the building response can be different than the ground motion. So in general, the PGA is not same as the spectral acceleration, and the reason being that the building is not infinitely rigid. Actually, the real life buildings are flexible in nature. So you might have the question like when the PGA would be same as the spectral acceleration. So what could be that situation, right? So this situation arises when the structural rigidity is infinitely or extremely high. Theoretically, it is infinitely high. That means the structure, due to its extremely high rigidity, can't even undergo internal deformation, and hence the structure would shake or move in unison with the ground. So the structure with infinitely high rigidity has the infinitely high natural frequency and thereby zero or close to zero natural period of vibration. Now, if you see the graph here, the spectral acceleration value against the zero natural period is around zero point 0.7 g, and this 0.7 g value is also the PGA recorded at the station. So that interprets that the structure with extremely high rigidity has almost same PGA and the spectral acceleration value. So we have overlaid the spectral acceleration graph of this station with the codal design response spectrum graph for this zone. You can see here, both are put together. This indicates that the spectral acceleration for this earthquake at this station exceeds the design response spectrum. Yes, the codal design response spectrum is constructed based on the design basis earthquake, that is the DBE. That means the MCE level further brought down to the DBE level by some factor. But still, the spectral acceleration curve is high and seems to exceed the target level for this situation. Similarly, there are many other stations from where the strong motion records and the data are fetched and the corresponding spectral accelerations are plotted. So this is the graph where all the spectral acceleration from various stations are put together, and these are all compared with the target design response spectrum specified by the code. Now here you can see that in most of the cases the spectral acceleration exceeds the design response spectrum. And among all of them, one of the station has got the PGA value of around 1.6 G. Now I'm talking about the PGA, not the spectral acceleration for this station. That means the spectral acceleration for this station is way high. It is around 2.5 G or even more than that. So we can take some inference that this earthquake was so strong that in some cases the design response spectrum as per the code could not suffice the actual demand. Now the second point is the building height. Now the building height, if you say the most of the buildings in those urban areas are mid-rise buildings, that is building having the number of stories in between 5 to 20. And if you see the response spectrum curve, which has been plotted, it clearly indicates that the building with the time period in between roughly zero point 0.5 to 1.2 seconds are severely damaged and collapsed, which are mid-rise building of 5 to 20 stories. So if you see the spectral acceleration graph, the peak spectral acceleration are in this period range, which significantly exceeds the design spectrum. So the next point is the non-ductility and the brittleness in the structure. Like most of the international design code, Turkish design code also specifies designing the concrete building structure relying on the ductility and the overstrength of the material to absorb the earthquake energy and avoid sudden collapse. So for this, the earthquake design load is reduced by a factor which we also call as the response reduction factor. But the collapsed building structure depicts a different story. So most of them were found to be non-ductile and failed like a typical brittle structure. So what went wrong? Okay, so the collapsed building were designed based on the reduced earthquake load, that is using the response reduction factor R by relying on the ductility and overstrength of the material used. But on reality, during the construction and the execution phase, enough steel and the confining reinforcement to meet the ductility demand were not provided. The basic ductile design philosophy is to survive the main shock and get out of the building safely. However, the collapses indicate that enough reinforcements were not provided as required by the code. So the designer and the constructor should have followed this code very strictly, but unfortunately, these are not followed on the ground. So this also indicates the poor and non-conformity in the construction practice. Fourth point is the seismic aftershocks. So this one is one of the most important reason for such scale of structural catastrophe. Now, the first shock of 7.8 magnitude was strong enough to weaken the structural strength of the building. Many of the buildings which still survived the first shock from collapsing, but there were many aftershocks, and one of them was big enough, like 7.5 magnitude. So these aftershocks further brought the damaged structure to collapsing. So here you can see there are so many aftershocks. So what happened on the ground was after the first shock, the large number of buildings developed the cracks, inelastic deformation in the beam and column joints, and got the building partially drifted from its position. And these structures are very susceptible to high P delta effect, that is the second order moment, if slightest of disturbance is further experienced. But the unexpected aftershock of huge magnitude immediately produced a high P delta effect in the damaged drifted structure, and that led to the overall structural collapse. So currently, most of the design code barely have any proper mention on dealing with the aftershock effect. So here, some more research work are needed from the engineering community to ensure that in future point of time, the building can be designed which can also withstand the seismic aftershocks. Fifth point, that is the old structures with poor retrofitting. Now, over 12,000 buildings have collapsed in Turkey alone, with few buildings in Syria, where dozens of buildings collapsed, including archaeological sites in Aleppo, that is one of the oldest inhabited cities. Many of the collapsed buildings were believed to be built before the year 2000. It was found that most of those old dilapidated buildings were not retrofitted properly, or even they were not retrofitted at all. So few reports show that the collapsed buildings which were out of its fitness were left out without proper retrofitting for several decades. The next is the soft and weak stories. Now, this is one of the most common issues with the building construction in the seismic prone zones. The open story at the ground level, mainly for the parking and some other reasons, are very dangerous to the overall building vertical stiffness regularity, especially if these conditions are not properly considered during analysis and design. The collapse showed that the building had many vertical irregularities like soft stories and the weak stories, especially in the ground floor where there were large openings. So the construction authorities must be very strict on checking the building horizontal and vertical irregularities, and they must ensure that the design conforms to the local seismic code. So, if we see the overall reason, so we have seen that although the earthquake was very powerful, but few of the things could be controlled. Like few more research is needed from the code committee, like revisiting the design spectrum curve, consideration of the aftershock effects, and so on. In addition to that, more advanced seismic warning stations are to be properly implemented. Now, most of the seismic warning stations which are already there rely on the P waves as they travel faster than the S wave, and this allows the sensor to quickly sense the powerful incoming S wave before sending the alerts to the occupants. Uh, in general, there is a gap of around 10 seconds between these two waves, depending on the distance from the epicenter of the earthquake, which is good enough for the occupants to take the safe refuge. But above all of them, the construction practice must be strictly followed. The authority must come up with some strictest measures and enforce the building regulation to stop the poor construction practice in the near future. So finally, just to add that the earthquake is in the hand of God, but mitigating the damage is in the hand of we engineers. So please let me know if you have to add any points and any suggestion that what went wrong with such a catastrophic damage in this recent Turkey earthquake.